All right, let's dive into one of the most fascinating parts of modern AI, how we're teaching computers to actually see. I'm not just talking about processing a bunch of pixels, but about getting a machine to truly understand what it's looking at through a camera.
So I want you to think about this for a second. A self-driving car has to, in an instant, identify every single thing around it. Other cars, people, traffic lights, you name it. And it has to do all that while it's zipping down the road. This isn't some far-off sci-fi idea anymore. It's a real, solved problem. And today, we're going to break down exactly how it works.
You know, when you or I look at a photo, our brains just get it instantly. But for a computer, an image is nothing more than a massive grid of numbers, pixels. So the first huge challenge is teaching it to go from just acknowledging that grid of pixels to genuinely understanding the scene inside it.
And this right here, this shows the huge leap we're talking about. See, basic image classification, that's step one. It can tell you if there's a dog somewhere in the picture. But object detection has to do two things at once. It has to figure out what the object is, and it has to draw a precise box around where it is. It's the massive difference between knowing what and knowing what and where.
And trust me, this is so much harder than it sounds. The algorithm has to deal with a totally random number of objects. It needs to spot a massive truck right up close, and at the same time see a tiny pedestrian way off in the distance. And get this, most of the image, like over 99% of it, is just uninteresting background that it has to learn to ignore, all while trying to find that perfect balance between being fast and being accurate.
So this constant battle between speed and accuracy actually created two different schools of thought, two competing philosophies in the computer vision world. You can kind of think of it like a friendly war between two types of investigators, each with their own special way of solving that what and where problem. Okay, so on one side you've got the careful detectives. These are your two-stage detectors like the famous RCNN models. What they do is they first scan the image and propose a bunch of interesting-looking areas. Then they go back and carefully analyze each one. They're super accurate. But then, on the other side, you've got the fast scanners. These are one-stage detectors like YOLO and SSD. They just look at the whole image one time and predict everything, the boxes and the classes all at once. They might give up a tiny bit of accuracy, but they are incredibly fast. And this timeline just shows you how ridiculously fast this field moves. The original RCNN was a huge breakthrough, but it was slow. It got better with fast, and then faster RCNN, but then 2015 happened, and this wild new idea called YOLO, which stands for You Only Look Once, completely changed the game. This whole fast scanner idea wasn't just about going quicker. It was a total shift in thinking that made real-time object detection possible, not just in some research lab, but on devices you and I use every day. And now, modern versions like YOLO V8 have just taken that idea and optimized it like crazy.
So how do these things actually work their magic? Well, it's not magic at all. It's really just a collection of super clever engineering tools, each one designed to solve a very specific problem. Let's peek under the hood at a couple of the most important ones.
Hey, remember that problem we talked about, seeing objects at totally different sizes? Well, the Feature Pyramid Network, or FPN, is the brilliant answer to that. The best way to think about it is like having a pair of binoculars with multiple zoom levels. It lets the model get a big, wide view of the whole scene, but it can also zoom way in to catch all the tiny details. That's how it can spot a giant bus right in front of it and a tiny little bicycle way down the street, all in the same image.
Okay, so after a model makes its predictions, it doesn't just give you one nice, perfect box for each object. Oh no. It actually spits out hundreds of slightly different overlapping guesses for the same thing. It's a total mess, and that's where non-maximum suppression, or NMS, comes in. It's this beautiful, simple, but absolutely essential cleanup step that sorts through all that chaos and gives you one clean, final answer.
And here's how that cleanup actually happens. It's super logical. Step 1, you tick all those messy prediction boxes and sort them by how confident the model is about each one. Step 2, you grab the single best one, the one with the highest score. Step 3, you look at all the other boxes and get rid of any that are basically covering the same spot. And finally, you just repeat that process with whatever's left. It's such an elegant and effective way to tidy everything up. But what happens when a simple box just isn't detailed enough?
Exactly. I mean, drawing boxes around things is amazing, don't get me wrong, but what if we need more? What if we need to know the exact shape of every object, every single surface in a scene, right down to the pixel? Well, that's the next frontier. So the first level up is called semantic segmentation. The easiest way to think of this is like digital coloring by numbers. Every single pixel in the photo gets a label. All the road pixels get colored road, all the sky pixels get colored sky, and so on. But, and this is the key, notice how it can't tell individual objects apart. See how those two cars just kind of blend into one big car blob?
And to fix that, we have instant segmentation. This is the next level. It doesn't just label every car pixel as a car. It also understands that this specific group of pixels is car number 1, and that group of pixels over there is car number 2. It identifies each unique instance of an object. This is huge because it means we can finally start to count the things in a scene.
And finally, we get to panoptic segmentation. Honestly, this is kind of the holy grail of scene understanding. It combines the absolute best of both worlds. It identifies all the general stuff in the background, the road, the sky, the buildings, and it identifies and separates out all the individual things, the cars, the people, the bikes. This gives you a complete holistic picture of absolutely everything in the image.
So now, let's bring it all back to where we started. Back to that self-driving car. Because out there, in the real world, all of these complex ideas have to come together and work perfectly under some pretty extreme pressure.
This number right here, this is everything. A self-driving car has less than 100 milliseconds. That's less than 1/10 of a second to see the world, process it, decide what to do, and then actually do it. This is why that whole debate between the fast scanner and the careful detective isn't just some academic argument. It has real life or death consequences. You have to be lightning fast, but you absolutely cannot afford to be wrong.
And let's be real, the world is a messy place. These systems have to work perfectly when it's pouring rain or foggy, when another car is blocking part of your view, in the middle of the night with terrible lighting, and in the total chaos of a busy city street. Every single one of these situations is a massive engineering challenge that pushes these models to their absolute limit. You know, it's pretty wild. In just a handful of years, we've gone from teaching a computer if a cat is in a photo to teaching it to trace the exact outline of that cat's fur. We've given machines a genuine, powerful form of sight. So I guess the real question we're left with is, not that they can see our world, what are they going to end up showing us that we've never been able to see ourselves?